So let's crank up Euler's method. And let's choose some typical initial conditions. And let's watch the behavior as time evolves. And here is a tracing of the carnivore variable. And what do you see? Well, you might be tempted to say, oh, that's an oscillation. And it kind of very much does look like an oscillation. It's going up and down. It has a rough period of around 100 time units in this model. And it looks kind of like an oscillation. And then you look at it more closely and you see, oh goodness, it's not an oscillation. And it's not an oscillation because look at the first big rise and fall. There are two little bumps on the up. Look at the second one. There's one bump. Look at the third one. There's 2.5 bumps on the rise. If you look at the fifth or sixth one there's 1, 2, 3 full-blown bumps on the way up. So the question, is this periodic? And remember, we're talking math here. The answer to the question, is this periodic, is no. It is not. You have a couple of bumps here and one bump here. And what does periodic mean? It means that there is a period, P, such that the system x of t f plus p is equal to x of t. And p is called the period. And is that the case here? Well, no. Because this is going to pick this value, and then this is going to pick a slightly different value. There is not an exact paper doll's repetition of exactly the same figure, which is what, of course, it would have to be if it was periodic. So the first thing we have to observe about this behavior is that it is aperiodic. That is, not periodic. So it's not an oscillation. It's a sort of kind of oscillation, but it's not really an oscillation from the mathematical point of view. And the other thing you have to keep in mind is these little squiggles, are these just kind of random noise from the measurement or caused by outside temperature fluctuations or something like that? And the answer is no, because this is a differential equation. There is no external input. There is no noise. There is no randomness. X prime equals f of x, y, z. Y prime equals g of x, y, z. Z prime equals h of x, y, z. These are perfectly deterministic equations. And they have no room in them for anything like noise or randomness or any kind of irregular input to the system. And we're sort of accustomed to thinking if we see irregularity, we think about irregular inputs. Oh, the sunspot cycles or the crop cycles or the this interference or the interference of radio stations, or we're accustomed to thinking about outside interference as a source of irregularity. But that's ruled out here. This is a differential equation with no randomness and no inputs whatsoever. And when I say not periodic, here we're arguing that it's certainly not periodic in the short term. This has 2 bumps, that has 1. But what about the long term? Could it ever repeat? And there's a very interesting answer, which is no. In the pure math, this tracing, if we let it go on for 2 years at this rate, it would never repeat. In particular, if you think about making the 3-dimensional trajectory in x, y, z space of the output of that model, what you would see, so you ask yourself, well, it's going to go around and around and around, and could it ever close? Could it ever create a closed loop? And the answer is no, because a closed loop is a periodic function. And there is your period right there, and then it executes the same, and then it executes the same. This is a closed loop equals periodic function. So if this is aperiodic, then that cannot happen. And we're now going to be inscribing a trajectory that can never close, can never become a closed loop. We're going to have to inscribe an infinite trajectory that never closes because it's aperiodic. And then the second point is, you'll notice that when I started drawing this thing, I drew this trajectory and then my hand went off the board and I went here because, of course, as you remember from a while ago, trajectories can never cross. They can never have a point in common. Because if it ever did cross, then this point would be on 2 trajectories, the original one and the one that just crossed it, and it would therefore either be periodic or it would be a violation of the fundamental theorem on existence and uniqueness, because you're going this way on this turn and this way on another turn. Remember the theorem that says 1 point, 1 orbit. If this self-crossed, it would be 1 point with 2 orbits, and we can't have that. So this is a kind of an interesting situation. We now have to inscribe an infinitely long line that never self-intersects. And to make that a little harder still, we're going to create another condition that has to be obeyed, which is the existence of what is called a bounding box. In other words, there is a box in state space such that you can prove mathematically that the change vectors on every face of that box are pointing inward. In other words, you can show that the trajectory has to be confined within this bounding box. So now here is your assignment. Draw an infinitely long trajectory representing all of time. Draw an infinitely long trajectory which never self-crosses and remains confined in a finite box. What could that look like? The answer is, what does the trajectory look like if it has to meet all of those difficult conditions, infinitely long, inscribed in a finite box, never self-crosses? And the answer is, it looks like this. So you stare at that and you say, well, that's interesting. That's certainly no equilibrium point. And it's not a limit cycle attractor either. The state point, if you follow the state point as it inscribes this jug-like or upside-down coffee cup-like structure, it's interesting because you see that it follows a certain pattern as it traces this out. And again, let's remind ourselves that this is X, Y, Z space. What you will see is that in X and Y, where the Z is now the vertical distance here, what happens is that X and Y undergo an oscillation with each other. And all the while, Z is growing. Z is growing until Z grows to a point where it suddenly crashes. And when it crashes, the system goes right back and does another bunch of loops, and then Z growing all the time until again Z crashes, comes back and repeats. And in order to follow the instructions that we gave it, it can never hit the same point again. And so the second time it comes around, and of course don't be misled by the fact that this is a two-dimensional projection of a three-dimensional trajectory. So of course it looks like they're crossing a lot, just like it looks like my arms are crossing, but they're not. It's just an artifact of projecting a 3D structure onto 2D, and that's the same thing that's happening here. These are not crossing points. It's going just over or just under. And then the second time around, it's going to find another path that's in between all of the previous points. Remember, it can never repeat a point. And then Z is going to crash, and it's going to come back down, and it's going to repeat another cycle, going around and around as Z grows until Z crashes. So we have the XY oscillator, and we have the ZY oscillator. And those two combine, and every time this comes around, we're going to sketch in always finding new points. And fortunately, there's an infinity of them, so we can keep finding new points to make this trajectory. Now, I want to make a technical point. I said, fortunately, there's an infinity of points. Of course, in a computer, that's not true. A computer has finitely many states. It can only represent numbers to a certain length, 16-bit precision or 32-bit precision or 64-bit precision. But none of those is going to work in the math, because that means you have a finite number of numbers that can be represented in your computer. And therefore, as t goes to infinity, you are sooner or later going to have to repeat one of those old numbers, because there's only finitely many of them. But that's not true in the pure math. In the pure math of this differential equation, it can be proven that the trajectory never repeats, never self-intersects, never repeats, never forms a closed loop. So we're going to try, we approximate that here by having our computer work to very high precision, so-called double precision arithmetic. We have the computer work to very high precision, and it's able to draw in for as long as we care to look at it without actually hitting the same point twice. So here is an example of a trajectory that, as we saw, creates a very interesting pattern in 3D. And that's, incidentally, it's another reason to say that although this is irregular, it's not completely irregular. It's following a pattern. The x and y are oscillating while z is growing, and then the z crashes. That's especially clear if you look at the trajectory here side by side with the 3 time series tracings of x, y, and z. And you see how coordinated they are. The oscillations in the 2 tracings at the bottom, the orange and the green, those are herbivore and plant. The plant is green, the herbivore is orange. And you see what's happening. There are oscillations in the herbivore plant system that correspond to the scallopings as the z variable increases. Then the z variable crashes, and corresponding to the period in which the z variable crashes, you see that the x and y stop oscillating with respect to each other. So this is a coherent pattern of movement. X and y oscillation, z grows, kills the oscillation, x and y oscillation starts again. There's a causal story here. There's a pattern to the behavior, which makes sense from the point of view of asking what does the differential equation represent. And this object is a new kind of object. And this phenomenon is a new kind of phenomenon.